Hi and welcome to MSc. In this video we're going to be looking at solving for tension in a pulley problem, and we'll use the example of two hanging masses to do this. So in a previous video I solved this problem. If you haven't had a chance to check out that video, I'd recommend that you do that first. But here's the solution to two hanging masses. We found a net force, found that tension canceled, and we found that the acceleration of the system was 4.2 meters per second squared, and we called this a forward direction, where it's down on the larger mass side and up on the smaller mass side. So the question then becomes, how do I find the tension that's in that string or rope if it cancels out of this problem? So that's what we're going to look at here. And so what we need to know from our previous work, or what the question you'd have to do prior to, is you'd have to find the acceleration. So we had already found that the acceleration of this system is 4.2 meters per second squared. And I'll say that's the size of it. So I won't worry about direction here. So I'll use the absolute value symbol to say we're just looking at the size of it here. Okay, we know it's down on this side and up on this side. And it turns out there's actually two ways to solve this, and they're both completely valid. And I'll do the one that I prefer, but I encourage you to try the other solution after. So I'm going to draw two free body diagrams quickly. I'll draw the first one here, free body diagram 1, for this first larger mass. So we draw it as a point, and we draw a weight vector down for the weight 1, which is the force of gravity. And then I'll draw a tension vector pulling back up, and I'll make sure I have it as smaller than my weight 1. Then let's repeat the process here for free body diagram 2 to illustrate what's going on. And my weight 2 is smaller because it's a smaller mass, so I'll draw that, smaller. And then I'll draw my tension force, roughly the same size as the other one. Those should be equal. And my tension force here ideally should be longer than my weight 2, because I know that this is actually going to get pulled up. So what we have to do to calculate the tension is look at either object separately, and it really doesn't matter which one you use. If we think about this first weight, we can say, okay, well, tension is slowing the free fall down. If it wasn't for the tension, this object would just free fall down with force down of gravity, weight 1. This one, it's accelerating up, and what's pulling it up is the tension, right? And so the net force on this one is the tension subtract the weight. So I view this first scenario here as tension hindering motion, because even though it's moving down in this direction, it's not moving down with the full free fall force that it would have if it was just falling under its own weight. And this one, I picture the tension as the driving force, because it's actually what's pulling this object up. It doesn't matter which one you look at, but we're going to treat the masses separately. My personal preference is to look at or use this one. And the reason I like that is because it will keep the tension positive in our equation, which is just one less negative for students to worry about and one less place for them to get tripped up. So we're going to look at the net force, and we're going to look specifically at the net force here on object 2, again chosen because tension's what's driving the force or driving the acceleration on that side. Well, this will be the tension's pulling in that positive direction. Again, we kind of defined x as positive on this side up and positive on this side down. So we'll say x is positive here, and that means tension is positive, and the weight is negative because it's in the opposite direction. So I'll put the negative right there. This net force is mass times acceleration. And here, unlike in the previous example where we used the mass of the system, right, where it was the mass of both things, we are only looking at the one object. We're only considering object 2 for this diagram. So this is the mass 2. And that will equal tension minus the force of gravity, which is mass 2 times g, the acceleration due to gravity or the gravitational field strength. We are looking to solve for tension, so I'll move this term across the equal sign, making it positive. So I can say my tension is equal to mass 2 times the acceleration that we previously had calculated in that other video. And now we'll add this because this term becomes positive as we move it. So we can sub in now and say mass 2 was 3, the acceleration was 4.2, and then mass 2 is 3, and I'll use 9.8 again as my gravitational field strength. Okay, when we do this calculation, we will get 42, and the units here will be newtons. So this tension force is pulling up with a force of 42 newtons on this side. It will be the exact same value on the other side if you calculate it. And I encourage you to try that calculation, but watch for the negative tension because X is down, tension's up. And that will give you a negative tension. You just got to deal with one extra negative throughout. Okay? So that's how we work through finding tensions in ropes. Look at one object in particular and kind of treat it a little bit like an applied force, and then solve for it accordingly using your F equals ma, your net force. I hope this short run through about tension in a pulley example has been helpful. If it has, please consider liking the video and subscribing to the station. And as always, thank you so much for listening and watching.